welcome to the lecture 15 of week 5 of climate change extreme events course. In the last lecture we have talked about different types of methods for analyzing the, let's say, extreme precipitation time series data set or extreme temperature data set, and then we can also apply some sort of statistical procedures to identify whether we have any kind of particular statistical behavior. For example, we can test about whether we have a linear trend, whether we have a trend in the data set, positive trend or negative trend, or there is no trend at all, or do we have any kind of, let's say, breakpoints in the data set, whether the statistical property has been significantly altered after some period of time. We have also talked about, let's say, we can also construct these time series data set in your generalized extreme value distribution model or generalized Pareto distribution model to understand about, let's say, how the frequency and magnitude of these extreme events has been also altered. So, the most important question is, let's say, if you are talking about any particular extreme events, whether these extreme events are originating because of the natural variability or natural processes, or these extreme events are primarily the consequences of human led modifications, whether it could be your greenhouse gas emission, or it could be, let's say, greenhouse gas emission linked temperature rise, or maybe because of the land use land cover change at certain point at certain locations or region that somehow manipulates the hydrological or atmospheric component, and therefore it can provide alter the weather related processes or hydrological processes. Or let's say if you talk about some sort of human infrastructure development in certain region, which can also lead to a very significant change in the time series behavior. Let's say if you have more urban cover, we have more urban heating kind of issues, and therefore in those region in the city or where we have more urban areas, that might experience a very significant change in the temperature anomalies or profiles. So, therefore, it is very important to link that if we have extreme events which is occurring, and if it is occurring more frequently if you compare to the historical data set, what could be the leading cause of these change in the statistical property of the time series data set. So, in this regard, basically we have to think about attribution studies. Attribution is basically we are trying to link the extreme events time series to certain types of processes which can interfere, which can which can change the property of weather related processes or hydrological processes or earth surface processes like that. For example, anthropogenic driven climate change, where we are particularly looking at what is the role of human influence on climate extremes and what could be the future conditions. Let's say this is what we have so far understood in the historical context. What will happen if this particular type of perturbation will continue, or maybe you can think about the perturbation of these kind of influences may further increase in the future. What could be our climate extremes magnitude, frequencies, and how these relationships will evolve. So, therefore, in this way we have to be very clear about the attribution so that we can better manage those extreme event conditions. So, whenever we are talking about extreme events, we are essentially referring to, let's say, heat waves or forest fire, or the cyclone or drought, or let's storm surges or tropical cyclones, or let's say flood, or let's say dust storm. So, these are some of these events which are somehow linked with rise in the temperature, greenhouse gases, which is somehow linked with the human activities, vehicular emission, industrial emission, and other human led activities like that. So, this is where it is very important to have an understanding about attributions. So, in this particular lecture we will primarily focus on what is the understanding and principle of the climate change attribution. We will learn some sort of statistical and modeling approaches, briefly look at those approaches, how do we use those methods or approaches to attribute studies, for applying attribution studies like that. We will also examine some sort of case studies where these kind of approaches has been already used, and they have found the anthropogenic contribution or influence on certain types of extreme event processes. And then we will, towards the end of the lecture, we will also talk about what is the limitations and uncertainties in these attribution studies. So, what is exactly climate attribution? So, the definition of the climate attribution is the process of quantifying the human influence on specific weather or climate events. What is the role of human, or what is the role of human activities on a specific type of climate events? Let us say if you are talking about rainfall. So, whether extreme rainfall is increasing in certain region or it has been significantly decreased, what is the role of land use land cover conversion in that particular region? Whether is there any role of land use land cover change, conversion of forest land to the agricultural land or barren land or urban land, has any implications on the rainfall pattern in those areas? That is what we are actually where we have to look at the climate attributions, and we have to quantify the human influence on the specific weather or climate events. So, the key questions of these climate attribution is, did climate change make an event more likely or severe? Primarily when I am saying climate change, we are referring to the climate is changing because of these anthropogenic activities, particularly GHG emissions. What proportion of events risk is due to human activities? Whether is it very high proportion of the risk because of the completely driven by the human activities, or there is some sort of natural balance between human and natural variability, and therefore it is a kind of a joint result or a joint event because of two different processes which are somehow interacting with each other and therefore giving you some sort of output. So, how do we do some sort of these analysis? We have observational based methods. We have let us say we have some sort of observational data record. We can try to look at, let us say, what is their overall statistical behavior through the time. So, in the initial time we have, let us say, a very moderate behavior, we do not have any significant change, but after some time in the modern climate conditions we see that there is a significant change in the temperature conditions or global temperature, or let us say we have also seen the local temperature of any particular cities. Then what we have to do is basically we compare the global temperature rise with the local temperature, whether these two processes are somehow let us say moving in similar ways, or the local temperature are more steep compared to the global temperature, or local temperature is more gradual compared to the global mean temperature, like that. We try to look at the assessment through the probability distribution functions, where what is their overall probabilities, characteristics of these different events, and then we try to look at different types of models, mathematical representations that let us say if there is a one human activities which are influencing the local temperature at a certain place, if we remove that activities, what could be the natural conditions, whether that natural condition would match with other regions as well, or if we are adding more human activities to the system, whether your rise in the temperature or any particular weather events will also likely to rise more steeply compared to the original conditions, like that. So, this is what we try to look at. We try to model the human impacts, we try to compare with our different climate variables, and then we try to look at what is their overall impact, like that. So far we have the statistical approaches called probabilistic event attribution, which is basically sort of fractions of attribution risk, which is FAR we say, or maybe we can talk about climate model based approaches, where we are comparing historical observations with the model simulations, or using controlled model experiment with natural versus human induced run, and then we compare. So, suppose we are running the model at a global scale, and we are saying in the model that just remove the component of vehicular emission from the model. What could be the rise of the global temperature? just considering the effect of, let's say, volcanoes, electromagnetic radiations which is coming from sun, land use, land cover which we have, or let's say some other natural processes which might influence the climate conditions or temperature rise. So, if we remove the human component from the natural model setup, and then we run again a second model where we add the human component, and we try to look at whether the actual data set is giving you exactly the same pattern when we adding the human role in the model. That is what we are also seeing in the observed conditions. In that sense, we can summarize, okay, the human are the leading cause of certain changes in the statistical properties of those events. So, the first process is called, statistical approach is called fractional attributable risk analysis, that is called FAR. So, FAR generally use measures the probability of natural versus actual event, where we calculate what would be the probability of the event when, if it is there is a natural kind of conditions, and what would be the probability of occurrence when we are actually the real scenario or real condition or historical observations like that. So, when we calculate these two types of probabilities and we take the ratio between probability of natural divided by probability of actual, and we will get some sort of number here. So, that basically FAR values will suggest what is the fractional attribution of a particular processes, let us say anthropogenic impact on a certain areas like that. So, for example, here we have two different statistical model where we have observed data, for example, historical period of data. Let us assume these conditions like you are measuring the rainfall in a certain location since 1850 till 2025. Okay. Now, you divide your data since 1850 to, let us say, 1950, which is more or less a pre-industrial conditions where we have more or less a very baseline period 1850, 1950, 100-year data. When we have, let us say, 1951 to 2025, it is more changes which we have seen. So, then we compare these two scenarios and we look at it, what would be the probability distribution function, and what is the event which is occurring at without human contribution or natural variability, and with the human contributions, and then we compare, we calculate the probabilities, and then we calculate what is the fractional fraction of the attribution risk in a certain region like that. So, this way we would be able to calculate what is the FAR for a heat wave, FAR for the flood event, FAR for the climate rainfall extremes, FAR for the, let us say, drought events. So many application we can do using the probabilistic models. Then there is another way, is basically the observational evidence, what we have just discussed that. So, if you have 1850 to 2025 data set, we can take the pre-1950, 1960 data set as our baseline period, and then the rest of the data is called let us say human drivers or human driven changes, and then we can basically compare these two different data set and then look at it, what is the changes happen in, let us say, mean behavior, standard deviation, or let us say some sort of probability variations like that, and that is basically we can look at it how these different has been changed like that. So, for example, where we will get this data set? The data set can be collected from the remote sensing satellite ray analysis data set, which we have already discussed in the previous lectures. Instrumental records, let us say we have a point locations where we are measuring some sort of temperature, precipitation, sea level rises like that, or some sort of paleoclimatic proxies. It is a very important, a very important data set, because paleoclimate proxy data set can give you not only hundreds of the years record, but thousands of values, thousands of years of the record of a particular climate variability. So, one of the very important proxy is, let us say, tree rings. So, there are many trees who have these trees has a very long period of total lifespan, more than 500 years, more than 700, 800 years like that. So, we can use those trees as a we can if you see that cutting of a tree, there you can see there is a circle within that stem of the tree, a big stem of the tree like that. So, when you count these rings of a tree, you would be able to look at what are those years when this tree was exist in that particular location, and based on the rings thickness, whether it's a more favorable conditions or more some sort of very drought condition or heat wave conditions like that, you can also infer from that tree rings proxies. So, that can give you a very good record of climate change in a certain locations, whether this is a record by a tree itself, and we can basically collect these information. Another is ice cores, which can also give you a very fine resolutions, a long record where we can talk about how the temperature, how the precipitation pattern has been changed, looking at different types of isotopic ratios of those ice core records like that. So, these paleoclimatic proxies will give you a very long span of record, and based on that we would be able to look at, okay, what is the natural variability which is influencing your climate extreme at a certain locations, and what is the contribution of human activities in that locations like that. What is the challenges in observational data quality assessment? Regional variability in data availability, that is one of the issue. What is the regional variations, where we are taking the data set, whether it is coming from the homogeneous group upset of the group, or maybe if it is coming from the heterogeneous areas where it can infer. So, the point wise we have a very different data set like that. And secondly, the data availability. So, what is the data availability, how many times of the data set is available there, and whether the data available whatever we have can be suitable for some sort of probabilistic or modeling based analysis like that. Then we have limited length of high quality observational data, which is also a sort of data length record, and that is basically can sometimes pose a significant challenge in quantifying this kind of analysis. So, this is all about observational record. So, observational record might have some sort of missing data set, or there is no data at all, or let us say there is a failure of instrument, then we would not have any particular months of the data for that particular locations. That might possible. It's so because of these are the random errors like that. What is the alternative? Alternative is basically we can whatever the data we have in that particular location, we can develop the climate model, and then we can simulate the historical conditions, and then we can validate with our historical record, and then we can try to fill the gap whatever we have in the observational record. That is one way of doing these things. Or it might also be possible that we can go one step further. We can reconstruct the historical data set or record where we don't have the instrument at all at that particular locations. So, that can be also be done by these kind of climate models or hydrological models or different types of modeling studies in certain regions. Or maybe you can think about let us say if you have different types of climate scenarios, what would happen in future if certain types of processes which happening or let us say the emission rate will increase in the future conditions like that. So, that in that way basically these climate models are very important which can play a very significant role in attribution studies. What are the types of these climate models? We can use general circulation models, GCMs and RCMs. We have also talked about what is exactly GCM and RCM in the previous classes. We have also talked about what are their differences. For briefly, GCMs are very covers a broader region, a whole globe of the data of record, and then simulate the large scale phenomena. For example, ENSO, sea wave transfer from one place to another place, or let us say the temperature anomalies or rainfall pattern across the world like that. Regional climate models are more finer resolutions where we are looking at the climate variability of one particular regions. Let us say we are talking about Indian subcontinent, or we are talking about Chinese areas, or we are talking about some sort of Japanese areas or US based or European Union like that. So, where we can use the regional climate models and we can do some sort of these analysis. So, what is the advantage of these models? We can simulate with and without anthropogenic greenhouse gases. So, suppose we set up the model for the historical conditions, which we know that anthropogenic emissions are significantly impacted. We just try to turn off that component in the model and then we rerun the model again. That would be a kind of a natural simulations, and there we compare with and without anthropogenic greenhouse gases, what is exactly happened in that particular region. What is the strength of this model? These are large scale validations requires, we do that, and the mechanistic understanding, because we have a process based understanding of all this, therefore, it is a more robust kind of analysis. Weakness is, it might possible that some of these models are developed for a particular specific areas, but we are using for slightly away from that area, it might produce some sort of uncertainties. It also possible that in some sort of the component, for example, there are several model which are very good in simulating the ecological and climate interaction. There are several models which are very good in climate dynamics or atmospheric layerings. So, therefore, it has to be some sort of what is the more advantage of different processes and how we can get reliable results out of it. So, the one possible solution is we can take ensemble mean and we can try to look at how the ensemble means are doing like that. So, these are the temperature data set which tells you about the historical observed data set, historical observations or model predicted values, and then we have for different climate scenarios what is going to happen in the future. So, then we can think about switching off the human contribution, and then we can rerun the model and then we can compare if there is a some sort of control in the greenhouse gases emission, what would be the our overall temperature rise in whole globe like that. So, this is what the approaches are which we can use for attributional studies. Now, we will talk about some sort of case studies. For example, case study 1 is heat waves, where we are talking about European heat wave of 2003. So, here this particular analysis applied the FAR estimate, fractional attribute ratio kind of analysis, where they found that human influence doubled the probability of occurrences of these heat waves. So, we can run the model or we can have the data set for natural and human made contributions like that, and then we can calculate FAR and then we can suggest what is the influence of human in those regions like that. How do we use these results? We can use the early warning systems, heat action plan, and we can mitigate using these different implications, so that we can minimize the risk which are associated with the heat waves currently and what is likely to happen in the future conditions like that. Then we have extreme rainfall and floods case study, where we are talking about 2017 Hurricane Harvey extreme rainfall, where what is their finding is basically during this particular event the moisture content has been increased due to the climate change intensified rainfall, and therefore, we have some sort of urban flood issues in those regions like that. So, it is a linked event one by one, and that is basically created a more catastrophic conditions in those regions like that. What is the policy implications? Urban flood planning or resilient infrastructure planning to actually mitigate all these different types of events, or let us say control the risk associated with these types of events like that. Then third case study is wildfires, where we are talking about Australian wildfire of 2019-20. So, the scientists have used the rising temperature and prolonged drought linked human activities because of the human attributions, human activities which has been changed the temperature rise or the drought occurrences, and that is the what is the linking of these extreme events linked human activities is basically the forest management or wildfires situation in different parts of the Australian regions like that. What is the response strategies is basically emission reduction or basically mapping those areas which has been already been vulnerable or which is likely to be more vulnerable in the future conditions like that. So, this is how basically one can look at it the different that rise in the temperature, and that has been linked with our human activities like that. So, these are the case studies where people have used the attributional work in different parts of the world to look at it, how the human activities are primarily responsible for intensity or magnitude of these extreme events across the world, so that we can have better management or policy plans like that. What are the challenges? Of course, the incomplete historical records, measurement biases because of the failure of the measurement devices like that can create some sort of errors in the data. What is the model uncertainties? Sometimes the resolutions, parameterizations are very important steps. If we there are some problem in these that can produce some sort of uncertainty in the model. Event complexity, let us say if we are talking about only one particular variable, but it might possible there are multiple variables are also influencing, therefore multiple contributing factors beyond climate change can be one of the important parameter in that event complexity we have to talk about. How do we reduce the uncertainties? We have to be very sure about the data and information whatever we are using, finding new relevant information, conducting additional observations, or maintaining or extending meteorological or hydrological observations, improving data availability or creating global data set like that. Climate models, we have to improve the understanding and parameterization of the process implemented in the models. Maybe we can use the GCM and RCMs with the finer resolution to reduce the scale mismatch, or we can improve the testing of climate models GCM and RCM with the historical record observational data set to basically look at their variable the validation or their behavior, overall accuracy of the model, or maybe we can use the ensemble of the climate models to to overcome the issues of different processes or different resolutions or different uncertainties, or maybe we can include more human influence, irrigation, land use, land cover change, a behavioral response analysis in the climate models to basically address more robust way to quantify the human impacts on different types of your climate extremes like that. Or maybe we can use hydrological models where we can improve the understanding of process implemented in the model. We can use the climate input data with finer resolutions in this hydrological model to simulate, let us say, floods and droughts, or let us say different types of hydrological conditions which might favorable for different types of extreme events. Comprehensive evaluation of these models using the multi-impact model approach, where we are not only focusing on the hydrological model, but we can also take advantage of your climate driven models or socioeconomic based models, or let us say ecological based models, where how these models are interacting with each other to get an more insight about what is the overall role of human activities or attributional studies on these different processes like that. So, when we are talking about the hydrological model, it is very important to assess their performances, applying weights or some sort of procedures to look at whether your model is actually good or not. We can also work with human influences with the hydrological model to include whether land use, land cover has any significant change in the discharge, for example, or drought conditions or flood conditions, or let us say dam building activities has any particular impact on hydrological processes like that. And the last is basically sensitivity analysis is very important, and when we have all these things we can have a very good observational or model based assessment that can be very useful for assessing the role of human activities or attributional studies in a particular regions like that. What is the policy and societal implications? When we have all these information, we can suggest for planning, regulatory and instrument that can be used for financial resource allocations, stakeholders and political leadership that can basically assess the situation, and then what would is happening in the future impact, what is how do we mitigate them, the objective settings, and then actions planning and pathway settings, assessment of selection of actions, which processes is very prone to, let us say, some sort of climate driven processes. We can look at those critical processes, and then we can try to mitigate some sort of implementation strategies in those areas so that we can mitigate the effect. And particularly after that, we have to monitoring and evaluate whatever we are suggesting in certain regions like that. So, this is what is policy and societal implications. This way we can improve the infrastructure planning, we can improve the land use, land cover planning, and for in the context of the climate change driven processes. What is the key takeaways? Attribution studies provides insights into human influence on climate extremes. FAR or statistical based approach or climate models are essential tools in detection. Then we can use, once we have already developed these approaches, FAR based or climate model based, we can provide to the policy decision making that can integrate these attributional findings for further risk managements like that. So, in the next lecture we will talk about during week 6 risk assessment and return period calculation, and for today this is for today's lecture. Thank you so much for your attention.